My name is Sean Kramer, and I will be discussing my year-long research on the topic of security through static binary rewriting. Here, we look at the first step in the implementation of security, which is data type and variable detection from executables. Memory corruption bugs are one of the oldest problems facing C and C++ developers. The lack of type safety allows attackers to exploit vulnerable functions and insecure coding practices to hijack the control flow, leak information, or to corrupt the program. Currently, the existing defense techniques suffer from a variety of different flaws that limit their adoption within industry. These drawbacks can include an enormous amount of overhead or a high rate of false negatives or false positives, which limit their effectiveness of stopping all attack vectors. Even the countermeasures which have been adopted, such as shadow stacks, stat canaries, and address space layout randomization, do not fully guarantee complete security. Recently, a promising topic in the field of cybersecurity is incorporating static binary rewriting as a method of security. A new feature from Intel is their memory protection extensions, which extends the x86 ISA to include instructions that provide a form of memory bounds checking. Though this can be implemented in newly developed applications, legacy software cannot take advantage of these features. Another problem with legacy software is that the source code is usually not available, leaving only the binary as a means of program analysis. In order to effectively implement security to legacy software, the binary must be disassembled and analyzed dynamically during runtime or statically, which is after compilation but before runtime. For C and C++, software bugs fall into two categories. They can either occur in relation to space, a spatial error, or in relation to time, as a temporal error. Regardless of which error is utilized to create an exploit, they both share the fundamental concept of corrupting memory via the misuse of a pointer. In Figure 1, we can see a simplistic flowchart documenting how spatial and temporal errors are caused and the steps that can be taken to create various attack vectors. The goal of this research is to implement security of binaries in a static manner. By disassembling a given binary, identifying potential vulnerabilities, inserting security checks around these vulnerabilities, and recompiling the patched binary while maintaining the original functionality. The initial step in this procedure is to identify variables and data types from an executable, which is what will be detailed here. Our design incorporates the capstone disassembly framework, which performs a linear sweep algorithm to disassemble a binary back to a given assembly language. We chose to work with x86-64 due to its widespread use in modern processors. We do make some assumptions. One is that the binaries are unstripped, meaning that the symbol table is present. The second is that the binaries are compiled with GCC without any form of optimization. The flowchart in Figure 2 documents how we extract all relevant information about an executable. Here, we retain the symbol information for the purpose of identifying global variables along with function entry and exit points. Relocation information is retained to recognize library functions which reside in the program. Finally, all program sections which are flagged as executable are retained, but we exclude library functions that are placed into the program during compilation. These functions, along with any function created by the programmer, are held in the text section. But by matching function signatures to those found from the symbol table, we are able to interpret what functions are created by the programmer and discard those which are not. From here, we disassemble functions and parse the assembly code line by line utilizing a method of pattern matching to identify variables in their data types. This process is provided in the flowchart in Figure 3. When encountering an instruction which corresponds to the creation of a variable, the line number, data type, and whether it is a local or global variable is stored within a hash table. The preliminary results show that this approach is successful at identifying all local, static, and global variables from a binary. The patterns which are discovered are as follows. All global variables are provided from the symbol table. Uninitialized globals are located in the BSS section, whereas initialized globals are stored in the data section. Statically allocated variables, which are not initialized to a value, are also a part of the BSS section. Local, non-static variables follow an instruction pattern defined in Table 1. Essentially, for x86-64, a move instruction with a given offset from the base pointer corresponds to the creation of a variable. The data type of these variables are indicated by the suffix of the move instruction. For example, a move instruction with the suffix L would indicate an integer variable had been created, but a move instruction followed by the suffix SS would indicate that the variable created was of type float. Unique to x86-64 is the set of 8 floating point registers. These are specified by the use of the register with the name XMM followed by the number 1 through 8. The use of these registers can help distinguish floats and doubles between other commonly used data types like int or char. Long doubles can be recognized from the pair of assembly instructions FLDT and FSTPT. For pointers, a load effective address instruction is first used, followed by a move instruction. Since pointers do not vary in size, the suffix of the move instruction is not relevant. Structures cannot be explicitly defined, but incorporate a method known as byte padding, meaning that when a structure is created, the members will be allocated in succession. With this in mind, it alleviates the complexity of understanding when a structure is created and when there is a series of local variables created. Unions are similar, but individual members of a union can be distinguished by seeing if multiple variables map to the same address in memory, identified by their offset from the base pointer. Lastly, the identification of dynamic variables. There must first be an invocation of either a library function such as malloc or realloc. The value given to the dynamic variables following one of these function calls follows the same instruction pattern as local non-static variables. In conclusion, this approach provides a straightforward method of identifying variables and their data types from an executable without the need of source code. It is the first step towards the goal of implementing security in binaries. As for future work, there are many options that this research can go in. One idea could be to increase the complexity of binaries by removing the symbol table or adding compiler optimizations. Another avenue can be the identification of function prototypes, such as the parameters and return value. Lastly, another option can be the construction of a control flow graph from the binary and implementing a form of control flow integrity based upon the return values of each function. Thank you.